Okay, welcome back for our final video on photosynthesis. This is going to cover the light-independent reactions, and it is going to talk a little bit about photorespiration. Okay, so I want to remind you where we left off. We left off with producing ATP and NADPH. Those are going to become important in this part of photosynthesis. So the light-independent reactions, as the name suggests, is where we don't need light. Light does not need to actually show up at all here for us to be successful in making glucose from the CO2. But you do need to understand that 1, Calvin cycle is another name for the light-independent reactions, and 2, that it proceeds in 3 steps. So 3 general steps: carbon fixation, carbon reduction, and regeneration of RUBP. So this is the overview. And if you could understand this, you're in really good shape. Now, I'm going to tell you that there are lots of steps that we're skipping because it's just beyond what this course requires. But know that there are lots of steps. Everything always checks out. I promise you that we're not making up math or we're not making up steps. We're just skipping some stuff to make it a little more simple. But the first step here is carbon fixation. Carbon fixation requires CO2 to attach itself to a 5-carbon molecule called RUBP. Now, we talked about RUBP a little bit in class. It stands for ribulose bisphosphate. I don't expect you to know that, but I do expect you to know what RUBP is, and that it is a 5-carbon molecule that is going to attach to CO2. The enzyme that catalyzes this attachment is going to be called Rubisco. Rubisco is a really cool molecule, which we'll talk about a little bit in a second, but you really need to understand that it is attaching this 5-carbon molecule to the single carbon molecule of CO2, and that forms a 6-carbon molecule. Now, wouldn't it be awesome if we could stop here, because glucose is a 6-carbon molecule, and yes, that would be awesome, except for then we'd very quickly run out of RUBP. So we're going to see what we actually have to do. Now, the second part of carbon fixation is we split this 6-carbon molecule into 2 3-carbon molecules called 3-PGA. It looks like this. Now, Rubisco is actually a really cool enzyme, but there's a couple of things I really need you to know about it. One is the function that it takes carbon from CO2 and fixes it to RUBP. That's really important. That's this main thing that I need you to know. But I also want you to know this is the most abundant enzyme on Earth. I think that's pretty cool. It's a nice piece of trivia to know. The second phase is carbon reduction. Now, this is where we are going to reduce carbon, as the name would suggest. And now there's some steps that we're skipping here. I know that the chemistry would be a little too difficult for this course, so we're not going to get into it. But these 3-carbon molecules, 3-PGA, are going to be converted into different 3-carbon molecules called G3P. And you also need to know that PGAL is the same as G3P. You're going to see them in both ways. I think your POGL packet uses PGAL instead of G3P. But I do need you to know that they're the same molecule. Now, it seems like this shouldn't take a lot of energy. They look like they're the same molecule. They're not. There's a lot of interesting chemistry that goes on here, and that is going to take energy in the form of ATP, which came from the light reactions, and is going to take reducing power from NADPH, which also came from the light reactions. So NADPH will drop off its electrons. It will give it to an intermediate that will ultimately turn into G3P, and then since it dropped off those electrons, then it turns back into NADPH. Now, NADPH and ADP can go back to the thylakoid membrane and then be converted back into ATP and NADPH for this cycle to continue. So this is carbon reduction. The last phase here is RUBP regeneration. So this really is more of a math thing than anything else. But because we had 2 3-carbon molecules, of G3P, one of those gets saved, and it will join this pool of G3P to ultimately go make glucose. The other G3P molecule is going to be recycled to form RUBP. Now, you might be doing some math here, and you're thinking, wait a second, that doesn't work. 3 carbons can't make 5 carbons. Sorry, I just had a coughing fit. But if you saw that math and you think that it doesn't check out, you'd be right if we just had one molecule of CO2. And so we really should be thinking of this in larger quantities, more like in bulk. And so this is what would happen if we only had one CO2. It doesn't work. Now, if we have 3 CO2, it works a little better because now I have 3 RUBP and 3 CO2. Well, RUBP is 5 carbons, so that would be 3 times 5, that's 15. And then 3 CO2, there's 3 carbons for 3 CO2. That means then we'll have 3 6-carbon molecules. And then that means we'll have 6 3-carbon molecules. We spend some ATP, we spend some NADPH. One of these G3P gets saved to go make glucose. The other one is, or the other 5 are recycled. If we have 5 3-carbon molecules, that is going to be 15 total carbons. That means that we can regenerate RUBP, but we only get 3 of them. 3 5-carbon RUBPs is 15 carbons. 5 3-carbon G3Ps is also 15 carbon. So that looks like this, if you're trying to follow. Now, you might also have noticed then, well, wait, 1 G3P is not going to make a glucose, and you're exactly right. So instead, I need 6 CO2. So I take 6 RUBP. 6 RUBP is going to be 30 total carbons because there's 5 carbons per RUBP. There are 6 CO2s, which means we have 6 carbons. That means that I can make 6 6-carbon molecules. That is 36 carbons. Now I split those in half. I'm going to have 12 3-carbon molecules. 12 3-carbon molecules is still 36 carbons. We spend a lot of ATP. We spend a lot of NADPH. We conserve 2. We take 2 of these. The other 10 are going to be recycled. 10 3-carbon G3Ps is 30 total carbon. We use all of those to regenerate RUBP. 6 times 5 carbon RUBPs is 30. The math now checks out. And all we got from that is 1 glucose. 1 glucose. So it takes a lot, but luckily they have a power source, the sun, in order to really fuel this whole thing. Now, not this reaction specifically, because this is the light independent reaction, but the sun powers making ATP and NADPH, which makes this possible. So I really want you to understand that it takes 2 G3Ps to make 1 glucose, which means that the Calvin cycle has to happen twice. Now, this pictured here on the right is showing the Calvin cycle 1 time. And so we get 1 G3P. To go through twice, that means we need 6 CO2. Now, you might remember that the overall net reaction for 1 glucose in photosynthesis is 6 CO2, 6 H2O plus light makes glucose and oxygen. So this is why, because we need 6 CO2 ultimately to make 1 glucose. Now, the Calvin cycle could stop just once and just take that G3P, because G3P is actually a really cool molecule. G3P is the starting point of lots of different molecules. It can be used to make glucose, which is what we talk about for photosynthesis, but it can also be used to make fatty acids. It could be used to make amino acid. It just depends on what the plant needs, but we just talk about it with glucose. But I do want you to understand that G3P is a very versatile molecule that can be used to make lots of different stuff. Okay, so generally that is the Calvin cycle. The last bit that I need you to understand is that the Calvin cycle does not occur actually in a circle. I know that we often draw it that way because it's pretty easy to understand it that way. But in reality, it's just occurring randomly throughout the chloroplast. And I don't want you to get too stuck on the idea that it's a circle. So that is the light independent reactions of photosynthesis. You already should have seen the light reactions. Those together make photosynthesis. Now we're going to quickly switch gears to be talking about photorespiration. Now, photorespiration is going to occur when the stomata close during the hot parts of the day. Now, it's okay if it closes for a little bit, but if it's closed for too long, the problem is we're still going to produce oxygen because that's one of the products of the light reaction. And the light reactions are going to keep going because the sun's still on, right? And so the hottest part of the day usually is when the sun is up. And so the light reactions are still going to occur. So we're still making oxygen. Some of that oxygen can be used for cellular respiration, but too much is a problem. And now we're also, because the light reactions are happening, we're getting ATP, which is good. We're getting NADPH, which is good. But then we go into the Calvin cycle, and we're starting to consume all of the CO2 because the stomata are closed, so they can't bring more CO2 in. Now, this is photorespiration. It is going to be when Rubisco, an enzyme, takes up O2 instead of CO2. And this isn't good for the plant. This occurs when concentrations of CO2 are low and oxygen is high. So this is pretty bad for the plant. We talked a little bit about how it evolved earlier in the course, but I don't really worry too much about its evolution, but I do need you to understand that this is a thing. This meme is a little silly, but I kind of like it. Okay, so this is photorespiration. It is where Rubisco is taking in O2 instead. And so we form these different products, the 2P glycolate, rather than what we want to make as PGA. So this is a problem. Okay, now I don't need you to understand the whole mechanism here, but I do need you to understand that it's bad for the plant and that it happens when the stomata are closed because we're consuming too much of the CO2 and we're producing a lot of O2, so Rubisco will start taking in O2 instead of CO2. Okay, that is everything for photosynthesis. I think you guys will be very successful, and I hope your studying is going well. See ya!